Welcome to 3D-RD-S. This is rapid software package which is used to calculate and estimate radiation absorbed dose and other related quantities to tissues after the administration of a radioactive product. The software being shown today has already undergone FDA clearance with 510(k) approval. This first screen here would be the login page to the software. After registering an account, you can insert your email address and password and sign in. The first page you'll see after signing in is the home page for your organization. In this example, the organization is called 3D-RD Usability Organization. If you highlight it, you can see other organizations that you are part of with the option to create a new organization. On the left-hand side, we can see details about the organization and the plan associated with the organization. For this example, the plan is an enterprise with 30 users and up to 100 therapies. Further down, we have options to look at archived patients on the bottom, archived therapies, and organizational members. Viewing the members, we can see everyone included inside the organization. Organizational roles are broken up into three parts. Owners are the ones assigned as the owner of the organization. Admins are assigned to manage all members inside the organization and all therapies within the organization. And members, regular members of an organization. Owners and admins can see all projects and all therapies and individuals associated with the organization. Members are part of an organization but cannot see any therapy unless specifically added to that therapy. Going back to home, we can now see in the center of the screen, we have two categories up top, patients and therapies. A therapy is a radionuclide that has been added to 3D-RD-S and is used to create data sets for patients. In order to create a patient, the patient must be first added to a therapy. For this example, we'll create a new therapy for lutetium-177. Once we create the therapy, we'll be able to fill out the therapy profile. 3D-RD-S allows you to set surrogate radionuclides as well as just the individual parent radionuclide itself. For example, if you wanted to look at the dose from something like copper-67 using copper-64 as a surrogate, you could set that here, like so. But in this case, we're just going to be doing direct imaging lutetium-177. If your particular radionuclide has daughters and you want to include those in the calculation, you can select this checkbox here. Once you set your parent radionuclide, the only other data you need to enter here are your selection of source tissues. For this particular example, we'll be using kidneys, liver, and spleen. Next, we'll be able to set the RBE values. Lutetium does not have an alpha component. There will be no alpha RBE to be set. By default, the RBE values for betas, electrons, and photons will be set to 1. Now that we've created our therapy, we can go and add a patient. We'll call this patient 1. For the gender, we'll set the gender to male. If desired, you can also include the patient's weight, units, and any sort of description you need about this patient. Now that we have our patient set up, we can go and add a treatment cycle. This cycle, we'll call it cycle 1. And we have 3 different input data types. We have time activity curve, which will be what we use today, but you can also use time integrated activity and time integrated activity coefficient. Selecting time activity curve, or TAC, we can now choose how to input our data. So for example, in this case, our pre-administered activity is going to be 7.21 gigabecquerels. Administration time has already been decay corrected. So this is 5, 26, 2020, 158. For this example, the administration time will be the same because we decay corrected it already, and we'll be using 4 time points. Now we've set up our cycle, we can start to add data sets. So we'll call this one dose. Because we're using an adult male, we'll be choosing the ICRP adult male phantom. If our patient is female, we could choose the ICRP adult female, or we have a selection of pediatric ICRP phantoms as well. For this particular case, we'll be doing mass correction as well as tumor doses. At this point, if we wanted to, we could also change the RBE values of the associated particles. For this example, though, we'll leave everything at 1. Going to the next screen, we can now add additional tumors or tissues if we so desire. In this case, we're going to add 2 tumors. Call this liver 1 and liver 2. Hitting apply, we can now see down at the bottom, we have a table set up for 3 tissues and 2 tumors. This particular data set has already been decay corrected to the time of injection, so we'll select this checkbox, and we'll be entering the time as relative to administration time. So we'll select this as well. By default, the unit for this, hours. The data itself is going to be in units of megabecquerel, and we won't be including uncertainty estimates. However, users have the option of including manual standard deviations, including standard deviations equal to the k times square root of the activity, or equal to the some percent value of the activity. Now for this example, we're going to be highlighting the time in this table across the top and selecting all the activity values for the 3 organs and 2 tumors. Hitting copy and going back, we can now click times and activities, and the values be automatically pasted in. Since we highlighted both the time and the organs, we needed to click this button here with both. If I tried just clicking activities, I would get a warning saying that the list shape doesn't match. This prevents you from pasting incorrectly shaped data to 3D-RD-S. Now we have our values pasted. We can go to the next screen where we can add a bit more detail about what our tumor characteristics are. So in this case, both our tumors, we're going to have a soft tissue composition with a density of 1.03 grams per milliliter, and the diameters are going to be 6 centimeters and 3 centimeters. For this next screen, we can add in mass correction by pasting the values that we've already copied before. We've now automatically gotten warnings on the left side. The orange warnings indicate that the mass that you've entered is differed by more than 10% of the actual ICRP phantom mass. And the red warnings indicate that the difference in mass is greater than 30% from the phantom mass. Once we've confirmed that these values are accurate and correct, we can still go to next. And just receiving the final warning saying that some of the masses differ by more than 30%. Now we can begin fitting functions to our TAC curves. We'll start into the kidneys, click on fit, and go to exponential washout. From the fit function on the right, we can see what was used. We can see the actual formula and the AUC or area under the curve, as well as the fit quality. Clicking apply and integrate, we can now see below what the integration looks like. And the table at the bottom is now populated for kidneys. You can see the TIAC is 2.07 hours. There are other fit functions available inside 3D-RD-S. So for the liver, if we tried to use the fixed half-life exponential washout and to fit, we would see that we can only select 1 time point. If we were to deselect all time points except the first, we can see what that fit function would do while ignoring 3 time points. Instead, we can go to by exponential washout, do the same thing, and we can see what that fit function would look like. Once again, fit function is shown on the right, as well as the formula, AUC, and fit quality. If we were to try to deselect a time point and fit again, we would get a warning saying we need at least 4 time points for the bi-exponential washout. Now let's go back to the exponential washout and see what that looks like. So here we can see that the fit quality is still fairly good, over 0.98. We can see the AUC and the fit function here with no additional warnings. So for this, we'll keep that for now, hit apply and integrate, and move on. Now let's say we knew there was something wrong with maybe the second time point, and we wanted to ignore it. There are several different ways we could do this. We could deselect this time point here, as we showed before, perform the exponential washout, and just use this. Or we can use a hybrid approach, where instead of including the first 2 time points, we'll hit fit and plot, have an exponential washout function over the last 2 time points. Now, instead of hitting apply and integrate, we'll just hit apply, and then we can go down to integrate. This gives us more flexibility on how we treat the integration process. So over the first 2 time points, rather than using a fit function, we'll use trapezoidal fitting until we get to the 3rd time point. Then from the 3rd time point to infinity, we'll stick with the fit function. And that would look something like this. Now hitting apply, we can see that we have the fit function on top, the actual integration that was used, and the TIAC at the bottom. Next, we'll look at the uptake and washout functions. So first, we have the exponential uptake and washout. Hitting fit and plot, we can see what it looks like here with no additional warnings, but a fairly good fit quality. Now, if we switch to bi-exponential, we can see that at this point, it's probably overfitting with a fit quality of 1. And that suggests that we should probably go back and use the exponential uptake and washout. Now, looking at the shape of these points, we know it's probably also going to be using exponential uptake and washout. If instead of selecting it from here, we can copy the values from the previous tissue, which was also using the exponential uptake and washout, which will allow us to go right to the fit. Once we filled out the 5 TIAC values at the bottom, we can now calculate the actual doses to the tissue. So on the far left, we see the list of the target tissues, which were all the target tissues included in the ICRP phantom. We have the absorbed dose coefficient, in this case in grays per megabecquerel in the middle, and the absorbed dose in gray on the right. If we wish to change these units, we could change them to milligray, for example, or megacurie, millicurie, update, and the chart is updated to represent that. You also have the option of changing what administrator activity you provided. So if instead of 7.21, if we change that to 8, we can update and see what the doses would be in this case. But we'll go back to the administrator activity. Now we have the chart at the bottom as well for visualization, and you can see that the 2 tumor doses are quite high compared to the other target tissues. If you wish to remove those from the chart, you can deselect the tumor doses at the top, update, and now you'll see the 10 highest tissue doses. In addition, you can also select to choose individual particle type if you want to see the individual contributions. and also RBE weighted values as well. Although in this case, because we're using an RBE of 1 for all the included particle types, there will be no change. Once you're finished and you're happy with the results, you can click Export, which will export everything that you've done into a single workbook. And then clicking Finish will save the data set. Now that this data set has been saved, there will be an audit trail following everything that is done. So if we click here, we can see the audit report. So today it was created and we can see everything that was included. Now, if I go back, edit this data set, and maybe change one of the fits, let's say for the spleen, for example, let's say we want to include all the time points, exponential uptake and washout, fit, now when we try to finish, we'll require to enter a change. For this example, we'll say we updated the spleen TAC. Now, when I view the audit report, I will see that it was changed. Going in, we can see the individual parts. Now we'll take a look at an example output spreadsheet. The output workbook from 3D-RD-S would look something like this. The first tab would include the dataset information, including the patient ID, patient gender, what radionuclide was used, who was performing the analysis, and other details. The input data would also be included. If there is mass correction, there'll be a tab for that as well, shown here, as well as integration and fitting results. Finally, there will be, in addition to dose data, there will be dose coefficients. However, if the data set was a TIAC input and no administrative activity was included, only dose coefficients would be available. There's also effective dose coefficient data, including at the bottom, the whole body effective dose. And then finally, the last two in this case are the decay values used for the physics calculations and the spectra. Now, if you are administered therapy manager, admin, or owner of the organization, you also have the option to now delete a data set if you so choose. You can change the owner of the data set, or you can copy it. By changing the owner of the data set, only the owner of the data is able to edit it. So even though this account is the owner of this organization, you'll notice that I am unable to edit any of the fields. However, if I change the owner back to this account, I am now able to edit the input data. This is very important because it prevents two people from working on the same data set at once and creating conflicts. And that is a general overview of the use of 3D-RD-S for patient dosimetry. Thanks for watching.